have understood how prompts are working today, what are the logic, and how transformers are getting used to generate those tokens based on the input prompts. Now I'm going to say what the theory behind it, how it works in a very nutshell. And in the assignments and all in quizzes, we will be able to get some insight about how it works more. So before we go into the details, we need to understand what is the pre-training and how many pre-training capabilities that we have in this particular generative AI model. The first one is unsupervised pre-training. Now, what do we mean by unsupervised pre-training? It means that you are training a neural network, maybe a autoencoder, where that the latent space of the encoding is a pre-training latent, and it is being used for representation learning mainly, like with influency loss or cross entropy losses or auto encoding the reconstruction losses. They are creating a representation which will be used in the downstream task, like with a label data. And this is what is called unsupervised, because during initial pre-training, there are no supervision technique signals are being used. It's purely unsupervised. Then comes supervised pre-training. The supervised pre-training is very easy. You already have the label data at the beginning. For example, ImageNet pre-training, which has the label data, and also it has a representations for that ImageNet or image kind of classes. Like Polo is also a kind of pre-training which had used this ground truth, and you can use those representations for downstream supervisions. Then it comes self-supervised pre-training. In the self-supervised pre-training, mainly the pre-training, the same like unsupervised, it is also use the unlabeled data, but the difference is that the supervision, with supervisions from the unlabeled data is being explicitly carved out in a smarter way and use that as a supervision during training, and that's why it's self-supervised. And just like unsupervised, it can be used in the downstream tasks with a supervised level data to fine tune it. Or, as you know, prompting, you can use this kind of zero shot learning or prompting for your uh, supervision tasks at the test time. So these are the three different paradigms of speed training that we know today. And what we are going to deal with is self-supervised speed training more in the generative AI domain. Now, I assume that all of you know how transformer works. It has an encoder, it has a decoder, and it has a connections between encoding and decoding. Now, when I'm saying pre-training, right now we have encoder pre-training, decoder pre-training, encoder decoder pre-training. There are many combinations. I'm starting with decoder only pre-training. So in a decoder only pre-training, transformer decoder as a language model is remove the cross attention sublayers. What is the cross attention sublayers? I'm assuming you know transformers, so the cross attention is basically because of the encoder and decoder relationships, right? And at each position I, the decoder generates the distribution of next token. In the last class, you just know how to do it, right? So at each position I, the decoder generates the distribution of the next token based on its preceding token. And if I write this as a probability distribution, it is as probability of with parameter theta given that x0 to xi token, right? And it leads to the probability of theta at I plus 1, because what is the probability in the I plus 1 stage that a token is getting produced given that it has seen the tokens up to 0 to I. Okay. Now, given a sequence of m token like x0 to xm, the loss on this sequence is the sum of loss of pretending over the position 0 to m minus 1. So it's every token is produced by this decoder only pre-training, given all other previous tokens are getting generated and they are contextual in nature. So there is a sequence of tokens. Okay. And therefore, if we have a gold standard, like what is that ground truth token would be, then as a standard machine learning techniques, we can definitely use the log of cause entropy and try to match them together to get the final loss. Now you see this loss is 0 to m minus 1. So m minus 1, why? Because we have observed till m minus 1 and we are trying to get what is the mth token, and we are going to get this minimization. And if we have many data, right, like X is belonging to a data or a document class, then all the data for all the token. And these are mammoth optimization, which the modern LLMs or modern generative or autoregressive generative model, they are solving. Now comes encoder only pre-training. Now what happens is that in encoder only pre-training, it combines the encoder with some output layers, right, and receive the supervision signal which is there already there in the data. So if you see in this particular figure, in the left side, you have these x1 to x4, and you have their embeddings converted into E1 to E4, go to the encoder, arrive at a softmax, give some self-supervisions there, like the way I was saying. So here the self-supervision is in the form of masking. I'll come back into the masking with an example. And once this encoder is trained, then it becomes a pre-trained model. Now you are using the same encoder with a different prediction network. Now the softmax is being replaced by a prediction network or for your desired task. Please understand these things because this is going to come in next in a contextual way, how today's ChatGPT, GPT, they are related on how they are going to work. So this pre-trained encoder is appended with a prediction network, and that prediction network is going to be useful for your downstream task, whatever the task. For example, chatting is a downstream task. For chatting, you need a token prediction, which produced by GPT, right? So prediction network is a chatting which is producing the chat, a meaningful, grammatically correct chat, and there's a pre-trained encoder which is, for example, is giving you the encoding or embedding to realize that. Right. So BART is an example of this kind of encoder pre-training where they mask out few tokens. So let's say the early bird catches the worm is a sentence. Now you can mask out the early, you can mask out the worm, and all these masked token has to be unmasked in the prediction. Right, and all unmasked tokens are used for predicting the masked token. So this is how it is getting encoding. So if you see in the left figure, so this X3 is masked. So this is one of the masked token or word, you can say, right? So how the loss look like in this equation, the probability that X2 is early, given that X means the rest of the sentence, CLS is a starting point, is a special token to say that, okay, I am starting a new sentence. The mask bar catches the mask, right? So given this as a sentence, what is the probability that it is early? Similarly, what is the probability that S6 is going to be 1, given that the same sentence? Now, these probabilities are getting defined or getting learned from the data set, like the way I show you in the summation. There is a data set, right? So machine is trying to learn from these tokens that what was my sentence, what is absent in this sentence, and how can I figure it out what is absent from the data set. So it is a high probability word or high probability token, and that is getting trained to this encoder. Okay. Now there is another class of pre-training, encoder decoder pre-training. So what happens here? So it's not a only encoder, only decoder. This is joint learning, And this is often used for sequence to sequence problems or question answering problems, right? So for example, say mixed encoder decoder pre-training like T5 model, and we have a translation problem. So translate from English, Chinese to English, right? So, or prefix language problem. So if I give a subset of a sentence like a puppies are frolicking, and then what the next part of the sentence would be outside the house. So CLS is the starting point of the first sentence and S is the starting point of the subsequent sentence. So it's a sequence to sequence problem, and then is a translation problem. Now how it works? It takes the encoder with masking and it gives you the entire things to be encoded. And in the decoder, in the mask bar style, you are just producing the tokens which are absent, right? And whatever the things are there already in the encoder as a word, you don't have to produce them because they're already there. So this encoding basically taking the entire thing at once and try to produce what is the highest possible token distribution that is available to the decoder. And this is being used in the encoding decoding prediction. The same thing is being also be done in the denoising based. So this all about different way of doing the same things. But in practice, what works, what doesn't work, you have to experiment out. So in this encoder, in the denoising autoencoding, the encoder is being fed by this particular sentence, the way I show earlier, and decoder is basically decoding the all tokens, not only the mux token, but all tokens. And the loss is over the entire sequence, not only on the masked tokens that are getting produced. So these are the difference. Now, what works, what doesn't work depends upon the way you are training, the way you have the data set, and it is the way you'd like to create the applications in the downstream task. Okay. Now, if I would like to categorize them, so this is a whole lot of literature in it. I just wanted to give you an idea what is the theory behind it and how the thinking process goes. So there are few categories. One is language modeling, which is basically auto-regressive generations, predicts the next token based on its previous context. These are token by token. Masked language modeling is randomly masks the tokens in the sequence and produce those tokens using the entire mask sequence. The way I gave an example. There is another one is called permuted language modeling, which I'm not showing an example. But what happens here, instead of masking, they reorder the input sequence. So they jumble it up. It has no meaning. But the network should produce a sequentially, semantically meaningful number of tokens so that a meaningful sentence can be produced. This is another way of training or creating the data set. And finally, denoising autoencoding, the way I told, the input is corrupt with the sequence and encoder decoder models are trained to reconstruct the original signals. So here the corruption is through masking. We are just omitting few words randomly, right? And you are basically creating the all set of words, not only the masked word, all set of words. If you are using only say masked word, then the loss is different. If you are using all the words, including mask and unmask, then the loss is different. But these are the generally four categories of pre-training tasks with defined training objectives that are being designed today. Obviously, there are many more, and you can also imagine more in your next papers or in your next research endeavors. Now, if I give an overview of what, how the terminology goes, so there are uh, few terminology which you need to understand. First is vocabulary, like the way we have a dictionary in our English, right? You know that there are definite number of words. So similarly, there is a vocabulary size. So in transformer, each input token is represented as an entry in the vocabulary V. So for example, overview of BART. Overview is a token, off is a token, BART is a token. These are all word level token, right? And this overview is a dictionary word, BART is a dictionary word. So you can create a digital representation of the word which which correlates to a dictionary index, right? So you can think for the understanding of easiness. So this is what the vocabulary is. How many vocabulary I have? Then embedding size. So each token is represented by DE dimensional real valued vector. So this representation is the computer representation. Computer doesn't understand what dictionary is. So you need to understand, you need to convert the vocabulary into an embedding. Then you have hidden size. So the hidden size is the sublayer of dimension. So you know this transformer has different layers, right? So and every layers has some kind of hidden size. So that particular thing is here in the hidden size. Number of heads. I hope all of you know that how self-attention works. Now in every self-attentions, even in multi-head self-attentions, you have to have number of heads, which is being used for projecting the queries. And this is generally greater than equal to 4. And FFN hidden size. So when I'm saying this hidden size is I'm saying that how much hidden layers within the FFN we are going to have. So if you see, this is a typical in the left design structure where I have this X corresponding to the entry V, and it is getting augmented with positional embedding and segment embedding. What is segment embedding? When we have a image, text to text translation or prefix sentence translations, then you know that what is the segment of the same sentence is in the input, and what is the segment of the of the same sentence is there as an output. So to get these two different segments in input and output of the same sentence, you need to have a separator. So this is an example. Like if I have a token CLS, it is raining separator. I need an umbrella separator. Now you have these tokens embeddings like X0, X1, X2, X3, X5 based on your favorite embedding you heard from the previous classes or somewhere. So there are different way of doing this token embedding. Now you have position embedding, like in which positions this particular sentence. I'm not going into the position encoding in this particular lecture, otherwise it's too huge. I hope you got what position embedding is in the transformer context and also in the LLM context. And then you have a segment encoding. You see the segment encoding EA is still the first separator, and the second separator onwards it is EB. So this is particular, this is for the first segment and this is for the second segment. All these three things are getting concatenated here for before going into the self attentions and layer normalizations. This is how the BART's encoding are getting trained. Now coming to the large language model, what happens here? So the goal of the large language modeling is to predict the probability of the sequence of token occurring that I told earlier. So if we have X0 to XM, the sequence of token, and X0 is a start symbol like S, what is the probability of the sequence is identified using the chain rule. And this is a chain rule. So why this is chain rule? Because every token is appearing once the previous token has already appeared. So I hope all you know this probability theory. So the joint probability of X0 to Xm is basically decomposed into a conditional probability given that X0 has happened. Now what is X1 given X0, X2 given X1, X0? You multiply them together and you are going to get the final probability of this particular sequence. Right. And if I take this log, then obviously this entire probability space becomes summations because these are all product. In the log space, they are all summation. And if I am able to train a neural network with these things, then the neural network should be able to produce a distributions over vocabulary V. Please remember this particular word. Distributions of vocabulary V. In the later point of lecture, this is going to be very, very useful if you don't understand here, because this is easy thing. Next one is a very difficult one to understand. So this is distributions of vocabulary V denoted by probability of something given X0 to Xi minus 1, right? And then the token prediction task is, what is that X belongs to V, V is the vocabulary size, such that my probability of Xi given X0 to Xi minus 1 is maximum. Remember, this probability is a distribution, probability distribution. So I have to take the output from the probability distributions, which is maximum. In the last lecture, you saw something similar to that in the implementation, right? And now, if I have to do it in the decoder only transformer, this is basically trained by maximum likelihood, right? That what is, because I am going to get the argmax, so it has to be through the maximum is a log likelihood. Now, as previously in the LLM, like I saw in the BART, but these are decoder only. BART was encoder. So how it happens in the decoder? The input sequence of tokens is represented by a d-dimensional vectors, right? So if you see that these are the x, if you follow my cursor, this is the x0 to xm is a token embedding, right? And you have these positional embedding and all. And now you go to the language model, and the language model has these L blocks, right? And each blocks has a self-attention modeling and a fully connected FFN modeling, right? So now every block has a normalization layer. Now there are two kind of principle which generally we use in the normalization. One is post norm. The post norm means you take the input f, you take the function f. I'm coming to the function later. You have the input, and the output of the functions is getting added up with the input. You know the ResNet, the way ResNet works. So this input, the function's output with respect to the input is getting added up with the input, and then you take the layer normalization. So it calls the post norm architecture. If you don't do that, if you take the outputs L norm and then take the input as an addition, then it's a pre-norm architecture. So both this post-norm and pre-norm architectures are contextual engineering. You have to play with your designs, that which architectures is going to give you a better loss or better maximum likelihood estimators in the training time. You just play with this hyperparameter and decide. Okay. Now, what is f? So f is a core function, right? So for the FFN layer, the f is multi-layer feed forward. Okay. For self-attention layer, the f is a attention, and that attention is nothing but a softmax of q kt to the power d plus mask into v. I hope you know all these equations because you guys are equipped with the transformer literature. The only thing is that there is a mask, and this mask is going to give you a control that what are the input is relevant to me and what are the input is not relevant to me. And you can decide that dynamically during training. Okay. And then you have the representation of heads. Every heads you have in the multi-head attention, you have different heads, head 1 to head tau, and every head is just a projections of q, k, and v. So all this q, all this k, all these v are transformed into their respective weights. Remember this. Now you understand how much complications are there. All these q, k, and v are projected to these respective weights, and these are all trainable on the J subspace. Once they are projected, you are getting a projected versions of head. So you got many such projection versions of head because head J is this. And now you merge all of them to get the representations of your final head, multi-head. Right. And then we have L transformer blocks. So these are all for single blocks, and you have this kind of L. And at the end, you have this softmax, which produce the distributions. Distribution, something given x0, something given x0, x1. You see in the right, these are the distributions from the hidden that you are going to get. And this is where you have to make a loss based on your next embedding. So this is a mammoth engineering and mammoth number of variables that are getting simultaneously optimized to make the token predictions useful through a maximum likelihood context. Now, this is one example. I'm saying mammoth. So this is an example how mammoth it is. If you see all these GPT, Llama, Cohen, and all, you see there are huge number of depth, number of parameters are is in billions. So every depth are different. They come up with this depth based on their empirical studies. They have this width, like the dimensions of the hidden vectors, and they have this number of QKV heads, how many Q and KV that they have, right? So everything has different depending upon the different parameters, and therefore if you see that there are different performances, right? Now these mammoth things are not getting trained as easy, just like in your 16 GPU, 32 GPU GPU machines. So it requires a lot of insights into it. And what are the insights? First one is data. So you have to be very careful about quality of data. It's not that you web scrap it and it's going to work. So you have to clean for the data which may contain errors or maybe inappropriate content. You have to curate them. Diversity of the data, because you are dealing with billion set of parameters. You must have as many types of data as possible. Otherwise, this is going to be overfitted. Right. And then the pre-training, these are all about pre-training, right? You are going to use it for some downstream task. So pre-training has to has more diversified so that the downstream task can be easily done. Bias in the training data, it should not have any class imbalance or something. So this data curations is very, very important. It's the most important in any decoder only transformer training for next token predictions. I would say 60 to 70% of the efforts that should go into this data. Privacy concern is a legal concern. There are a concept called personally identified informations like PII, like the star coders and all are basically creating a neural network to identify whether you are leaking some privacy or not. So these also part of data. So there are a lot of attribute data. These are the four important attributes which you should be very careful enough when you are implementing maybe a small LLM with a small set of data. Next comes model modification. So it's not that whatever I told in the previous slide, they are getting used every time on every such Llama, GPT, all model as it is. No, they have different model has different modifications. For example, we know that layer norms equation is h minus mu divided by sigma plus epsilon alpha beta are the trainable parameters. You define you take any hidden or variable. This is the layer norm. This is the layer norm formula, standard formula. But in a llama, they have get rid of mu, and instead of sigma, they have used sigma RMS. And how did they arrive it? I don't know. That is their insight. During training, they have found that this is going to save their cost, energies versus their expected outcome. Like FFN, feed forward. We know this is the standard FFN. Sigma is the activation functions, HW is the variable, B is the bias, and then again it goes to the another WF, and then the entire bias. This is what FFN standard looks like. But in Llama, there is no bias. They have get rid of bias. So this is their decision. Right. Now comes distributed training. So all such training, this maximum likelihood that I told in the previous slide, they are not getting trained into a single machine or maybe a single memory bucket. So what happens in the distributed training? There are different kind of parallelism. For example, data parallelism. So what they use, we know these are training objectives. This is how gradient descent works, right? Now, these training objectives are all in batches and they are all mini batches. So we can have many such workers, right? Like threads, where these mini batches are getting parallelly executed. And then we can join them for getting the final loss or derivative of the loss. This is how the data parallelism works. Tensor parallelism. Now you have all these W's as a tensor, all the weights. So we can always partition the weights like the way we are partitioning these W's and make these parallel multiplications row wise, right? Then we have pipeline parallelism. So I'm not going into the details here, but you can understand what happens. There are multiple GPUs that are getting trained simultaneously. Now, how that training happens? Suppose you have a batch B, you make that batch further divided into micro batches. So this BI1, so BLK is the kth micro batch by Lth GPU. So what happens is that B11 is the first micro batch. So every neural network is getting partitioned into 3 or 4 sub layers. So you know that there are layers, layer 1, layer 2, layer 3, layer 4. Let's take two, there are 2 layers, layer 1, layer 2. Now, so these are coupled. So there is a forward pass. The layer 1 output has to be the input of layer 2. This is how it works. Now, if I take the batches to be further subdivided into 2 or 3 micro batches, then what happens that I take the first micro batch, I make it, this is a micro batch. The BI1, listen to me very carefully. BI1 is the first micro batch of batch B, right? That is getting fed into the layer 1. I got the layer 1 input, I got the layer 1 output for BI1. Okay. Now that layer 1 can start producing the output for BI2. But when the layer 1 is producing BI2, my first BI1 output is already there from layer 1. So I'm going to the next GPU for computing layer 1 second output, the layer 2. Right. So this is how the pipelines are getting. So DeepSeek has done a lot of marvel engineering to minimize the gap. You see the gap between blue and the orange. Orange is the back propagation and blue is the forward propagation. So because there is a dependency graph in the forward propagations, the main KPI is to minimize this white space. The method which minimizes the white space, they are much more utilizing the GPU, multi-GPU well. And this is an open problem. And that is where the entire world is fighting for. How to maximize the GPU utilization, how to minimize the gap. Now you can come up with a maybe new algorithm or new way of data partitioning so that these gaps are minimized and you can publish a paper. Right. So this is a concept where the neural network is getting dissected into different layers. Every layers are being run on different GPUs. And because every layers is dependent on previous layers output, they are getting micro batched, and every micro batch output is getting fed to the input of the next layer by the next GPU. And this carries on. Right. And therefore, if you don't use this micro batch, then the number of white space is much more wider, much more higher. If you use micro batch, then this is slower. Now, how to make it happen is a challenge that a researcher or engineer has to solve. But this is part of pipeline parallelism. Okay. Then comes scaling law. So none of these methods works under a very small amount of data. Why? Because in 2017, this Hessness has produced a nice paper which shows that the error against the number of data size or data size data set size uh, comes drastically when the training is in the power law reduction phase. If you see in the as the training data side is low, the error rate reduction is not very low. So if you use a very less amount of data and then cry that I'm following all maths, all equations perfectly, implementation is error free, why it's not working? It's not going to work. And there is a study on this, right? So you have to have a certain amount of data set. If you go to the paper and read it more, and then there is a irreducible error. After that, there is no reduction of the error. And this is also is not a casting stone. You can still experiment on it and try to get more insight about the scaling laws. Then optimizing high performance computing, right? So we generally use 32-bit or 64-bit floating point data types, and it is a huge memory. So one commonly approach is use a lower bit size for or fixed point data types for representation. That's a very intuitive way of optimizing HPC. Then sequence parallelism. So you have KV cache, you have this K and V. Now partition this K and V. You remember that attention K and V. So partitions the K and V by rows, and then you compute this K and V row wise, which leads to beta ij. And then you independently compute the alphas based on this independent beta ij, because these are all parallel. And then you do the attention. So you are saving high performance computing memories and computations. And once all these alphas are available, then you see that these are the node, these particular things, these alphas are in node 1, node U, node NU. Once these are all parallelly computed, you compute this alpha ij. Once you have the alpha ij, you have the soft max and therefore attentions. So this is how you can optimize the HPCs. Okay, and all these LLMs have some certain kind of attributes in one of these parallelism and HPCs. Now comes efficient architectures. Now we know that there is a QKV, self attention, and it is the mother inventions for transformer, this self attention. But it is very space and time taking. So I told you to remember this masking, right? So what this masking does is that we don't have to use all the tokens, all the subheads or heads of K and V to be attended to. What if we discard something? What happens? That's an experiment, right? So, so one trivial way to do this is you discard all KVs which are beyond your query. You dataset everything. But the token that you are producing, you are just relying on the left of the token, not right of the token. So you are creating a matrix which is lower triangular, rest of the things are zero. And you can have other masking strategy as well, depending upon your experimentation. So here what happens is I am denoting this K less than equal to Y, V less than equal to Y. That means I'm not going to consider my K and V, which are beyond my current token I. So my current token I's predictions for decoder only, I'm just relying on my current previous K and previous V till the previous, right? Now this is sparse attention, and this all these sparse attentions, they have to be stored into KV, because till now I have made all this K and V computed for my token till I minus 1. So there needs to be stored somewhere in the memory, right, in the computer. And that storage is not a, this is the array storage, because you have multi heads, right? For every K, you have many copies. And K itself is also big because you have millions of tokens. So this is a huge space and huge computations. So one way is to bring back is use a kernel function which projects this Q and K into very uh, small dimensions, and then you and remove softmax like this softmax, right? Then what happens? You see, magically, this entire QKV attention becomes linear, and it is just a division instead of matrix multiplication. And softmax is there, not there, so you don't have to do all these juggleries. It's just a ratio. And how this U and V are getting tracked? U is a running average with value to be multiplied, and V is just the running average of the key. And query you are anyway projecting, so you just have Q with mu1 and Q with V1. You see Q with mu1 has Q into VI, Q into KVI. This is what the formula is, QKT with VI. And this is just query into this KT, the normalization. This is very easy. But obviously, I'm not saying that this is the only way to do it. But these are all choices. How you can think for your own architectures when you are implementing your own LLMs. Now, this is a pictorial representation of the same thing. In the standard self attentions, you have a query embedding, and you are attending all KV, all KV. So obviously, these millions of KVs, like the Gemini and all, have millions of tokens to be stored and all. So millions of these KV attentions is obviously going to get a very, very large amount of time and space. Sparse attentions, you are discarding some of them, and how you are discarding is your choice. Whether neural network is saying that I want to discard, or you manually discarding, is your intellectual capabilities or intellectual properties. That's your paper, right? And then this is linear attentions, where all these QKVs are getting formulated into one vectors, like the way I've showed, and you just attending it, right? And all of them obviously has a pros and cons. Now memory. So all this QKV cache needs to be reside in the memory for this decoder only transformer, and all this Llama and all does that internally, right? So one way is that I cannot store all these keys and values till point I minus one, right? So I may have a fixed memory, and whatever the fixed memory is size, and I only keeping only those KVs and discarding others. This is one way of looking window-based cache. It's a very default and intuitive way to do things. Another one is moving average. The way I'm storing this memory. All these memories are getting flattened up into the moving average things, right? Then it can come as a recurrent neural network. So it's not a moving average. I'm doing slightly better. You getting the sense, right? Slightly intelligent. So it's not that only averaging. I'm trying my own neural network to say that what will be my next embedding of the QV, which is going to be useful for me, or any hybrid. So I'm using neural network and also I'm using the current memory. That's a hybrid one, right? Now comes external memory. So external memory is where you are storing this Q value into a database. And once the query comes, you are retrieving that database from your hard disk to memory and try to use that contextually, appending with your memory KV, and then giving a convex combinations of how much you would like to give the priority to the database and how much you would like to priority to the current query that is there in the memory. And that combines the togetherness of the key value pair retrieval and then attention. And one important, I hope everybody knew this RAG. RAG is in this philosophy where you are giving an input context, what is deep learning, it search the data stores or documents, it create the nearest neighbors based on this embedding of the input context, the text, and this text are getting appended with the input and gives to the LLM. So that LLM is less hallucinating. It's giving more context. So it's a part of external memories. Okay. Now comes a very important concept called KV cache. So it is sharing across heads and layers. Now I am saying that till now I was saying every key, every value are for every query. I am having the projections. So if you see, if I have L layers, tau attention heads. I told you in the transformer, if you are very well versed with the transformer, you know there are multiple attention heads and there are L layers. So if L layers has tau attention heads and produce DH dimension output with M tokens, these are all variables. Now, how much space complexity you have? L dot tau dot DH dot M is a huge space complexity, right? Now, if I do window caching like the way I told earlier, then M can becomes MW, but it is not much less. Still, you have tau, DH, L to be figured out. Now, what can be done better? So, can we decrease the KV cache in other dimension? For example, maybe let's say tau. Tau is number of hits. Can we do something on the number of hits? Because number of hits is a parameter of tau and it is getting projected into W head, and there are J projections. This is a head J. There are a lot of hits. So for one query, there are a lot of query projections. There are a lot of K projections. There are lot of queue projections, right? So one way is that multi-query attention. What is that? Don't project key and value every time. Let's have K and V fixed, but let's have Q to be project every time. The head J, the J variable here is attributed to the Q, not K and V. What happens? You see suddenly tau goes away. So space complexity drastically decreases. And with window, it's even more drastically decreases because AM will be MW. So you are basically relieving the computer memory. You need less GPU. So this is what the invention is. Whenever you are training LLM, you have to look for where are those inventions? Where are those benefits? How can I make my number of GPUs less? Where are those maths? Where are those engineering? So those are the things you have to look for. And that for that, you have to do something on pen and paper, more on theory rather than on engineering. Come to the engineering code when your theory is more or less done with all orders and all. Right. So this is an example. You have one query, key, value. So each query is attending one key, one value. This is one query is projected on multiple. So these are all J's. Keys are also projected, values are also projected. So everything is projected. Right. This is how generally transformer works. This is how the multi-query is. So you are having projections of all queries, but the value and key they on the same without projection, only once. And this group query. So you basically do this kind of projection for a particular is a hybrid. So every algorithm has a hybrid structure. That's the standard intuitions of human being, right? So, but this is called multi-query attention. Okay, so now it comes a very crucial things. Till now, what we learn is how to create next token. Up to now, what we have learned is maximum likelihood in a large scale training with scaling laws and all, how the next token is getting produced and what is the space and complexity parallelisms can in engineering or in implementation people generally deploy. Right. Now, once that is done, what is alignment is? You have to align. Right. What does it mean alignment? Alignment means it's a process of guiding these LLMs, means the next token predictors to behave in a way that align with human intelligence. This next token is the next word prediction. So what I'm going to do with this next word prediction? What application I'm going to do with it? Right. So I need to give further guidance to the systems. This further guidance can be with human feedback or any other form of human preferences. Now human comes up. Right. Till now machine was only access and human was only curating the data for it. Right. Now this is the standard alignment stage. So once you have pre-training like this next token predictor with maximum likelihood, all these probability distributions you have learned. So you go for supervised fine-tuning. So you can see the pre-training as a GPT and SFC as a chat GPT. The chat GPT use pre-training as GPT and supervised with the chatting data set. And that becomes chat GPT. That is one way of doing instruction alignment. Another one is RLHF, reinforcement learning human feedback. This particular lecture doesn't cover the reinforcement learning, but if you are aware of it, then it is basically human feedback is getting inside the reinforcement learning value networks, and that value network is in and eventually guiding the supervised fine tuning. And that's why this RLHF. And then comes prompting. What you guys are doing today with ChatGPT. Soft prompting, hard prompting, instruction fine tuning, these are all in the prompting. Okay. So I'm not going to go into the prompting because I think there is a special sessions on prompting itself. I have seen this course structure, so I'm not dealing with prompting. Okay, so what is the supervised fine tuning? It involves the continuing of training of pre-trained LLM on a new task. For example, GPT to ChatGPT. And for that, you need chats as a input and output. So here, this is a paired data. X is the instructions and user input. Y is the output. For example, instruction is summarize the following article. In recent years, solar energy has been unprecedented growth, blah, 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 blah. And what is the summary of it? You give it the summary. So you are giving the instructions and user input, and you are giving the summary, and you are creating a huge amount of data like this for supervising your pre-training model. In the first slide, I told you that a pre-training model are getting supervised in the downstream task with the label data. And this is the label data. This is the connecting between my exactly first slide today with how the GPTs or how the LLMs or the next token predictors are getting fine-tuned through SFTs. So let's X0, XM be the input sequence and Y0, YN be the corresponding output sequence, like the way I have shown in the data. What is the training objective look like? Again, now it becomes conditional probability distribution. So Y given X. And if you see, this is theta plus. Why this is theta plus? Because we are starting with theta from the pre-training stage and try to get the incremental versions of the theta like theta plus. Now, if I go into the log probability, then the token predictions becomes log of probability theta yi given x, right? And y less than I. Till now, what is my x input? What I have already produced in my y, because this y is also token. Earlier was x was the only token because it was a token predictor. Now it is not only token predictor, but also it is given the input instruction and user input. So it's x and y less than I both are given in the probability distribution. But the problem is, this conditional probability minimization is not the standard language modeling problem. The way we train BART or GPT or decoder only transformer, this is now that we have designed so far, right? So what can be done? So what we do is that we make this particular X and Y pair as a minimizer of a joint probability distribution, because this is how sentence to sentence, you remember sentence to sentence predictions and all, these are all joint probability distribution. So I can train my machine with joint probability distribution. So the what cleverness I'm showing is that in the joint probability distribution, if I break this through, I can break this in the log of X plus log of Y given X. Now, in my training set, I can cleverly put that log of X as a 0 in the loss. And I only have this particular loss because I have the data for it. Who is going to give me the data? This particular data set. And less than I token that is getting produced. Right. So if I pictorially see the forward pass in my this speed training stage, when I'm supervising it, in the forward pass, I'm getting all this X token and I have these input x1, x2, x3 and output y1, y2. In the backwards pass, for this x1, x2, x3, I'm putting loss equal to 0. That means no gradient is coming out of this particular gray area. The loss is only going to come from y1 and y2. So I am making this conditional probability learning through the loss based manipulation. Okay. Fine. If we have learned this, then let's say we have to go for dialogue now. So what is a dialogue? Dialogue means LLM engage with the chat, right? Means sequential chat. It's not only I have static data x0, y0 and done. No. So we have x0, y0, x1, y1, xm. So I give some instructions. ChatGPT gives me. Then again I give based on that. Again ChatGPT gives me. So it is a sequence. Now how to train that? Right. So this formulation is a homework exercise for you or quiz exercise for you. Derive, given the particular principle, what would be the conditional probability that you would like to design and how it is going to be related with this loss manipulation. Right, that I'm not doing, you can do it as your homework. So things to consider for SFT in practice, SFT requires level data. It is still computationally expensive because we are going by the same KV cache, data parallelism and all. It can be regarded as a post-training because it's a downstream. Is not a original training. The pre-training was a token producer, was the original training, and this is a post-train. Okay. Now, given that as a SFT, now what is going to be part of the RLHF? Now, I'm keeping only one slide here, but this is not a one slide tutorial. It itself is a 1 hour, 2 hour tutorial. So what happens is that LLMs are getting generated multiple predictions. Now, when you use ChatGPT, you might see that oftentimes ChatGPT gives you two outputs and says which one is better for you. So this is what it is. They give you two prediction, and human as a user, you say that okay, this is good for me. So this is there's a reinforcement learning network going on at the back, which trains this reward model. And once this reward model is trained, then all of your loss minimization is also going to get that reward inside it. So how it happens? You first pre-train. There is a pre-training data, there is a supervised data, and pre-training and supervised fine-tuning, you get an LLM. Right? Till now, all good. We have covered it, how to do it. Now, once the LLMs are, this user input is being fed, LLM is produce multiple output, and you are going to give a comparison, which one is good and which one is bad, right? Now, this comparison data is used for another neural network to train, which is reward modeling. Reward means something is good and something is bad. How, like the way you are digitizing the token. So this is how digitize the preference model, right? And then LLMs, this reward is getting again fine-tuned and based on the human preference, and this training continues. So this is how RLHF works. This is a very, very abstract level view. I'm not going into the mathematical details because it takes its own lectures. Okay, fine. Now coming to a star coder, how does they implement it? So they takes 1 trillion tokens, 800, more than 800 GB cleaned, deduplicated data. Now you see this itself is a project, 80 plus programming languages. So this is how they are one of very, very small sample data look like. So this is how the raw data looks like. Now you have to create these tokens and all, right? Training, they use decoder only transformer. We know right now how decoder only transformer needs to be trained. 15 billion parameters, 8K tokens at a time, multi-query attention. I taught how multi-query attention works in the KV cache. Absolute position encoding. I hope in the positional encoding lecture, you know what are the defined kind of position encoding, rotation position encoding, absolute position encoding, relative position encoding. It predict the next token. Again, like the way I told what is the maximum likelihood formulations with all distributed parallelisms. 32-fold data parallelism. I told what data parallelism is. Tensor parallelism. I told what tensor parallelism is. Pipeline parallelism. I told what pipeline parallelism is. This is what is being done in the training. Now, all these things you can modify and come up with your own better versions of training if there is any value propositions in all these parallelisms and attention laws, right? Okay, and this is what this input token and target predictive token look like. So if you give this, it produces that. If you give this, it produces that, something that sort of. Now, after this training is done, it comes supervised fine tuning. Now the star coder has to produce exact codes. So this is the part of SFT, supervised fine tuning. It has a base model like star coder base, which is this particular training. It has 35 billion of Python tokens now. It's specialized for Python. Now this is specialized for tokens, not specialized for any domains. Now this is specializing, supervised fine tuning. The goal is specialize the model for Python programming. There is no RLHF involved, but it does this kind of BART-like masking, fill in the middle only, not exactly BART-like, but only not like BART is random. It's not random. It's only fill in the middle, right? Like suffix, return, middle. So result equal to XY, prefix, suffix, generate middle span, something that sort of. So given these and these, what is the prefix and suffix? And this is how this code-based data look like, and this is how this input and target look like. Okay, so I have covered more of these text-based things, and now let's next 1 hour or so we'll be going to the image-based generations, and this is completely different from what we have learned till now. Completely different. Now I started with something sentence in the text generation, that neural network trained to accomplish this task and produce distributions over vocabulary. That is very important. I told you to remember this. I don't know, some of you maybe forgotten by now, so I have given that again. So distribution is very important, and because this is text, the distribution is easy. But in images, distribution is heavily complex. It's not that easy. Right. So you can see we don't know what distributions and images are having because they are high dimensional data. And we don't know the data distribution of image. How do you know what kind of distribution? So you have a dictionary for words, Oxford dictionary or something. Is there any dictionary for images? No, no. So how to know what is the data distribution of image? It's impossible to know. How to know model distributions? Even more impossible. But what we would like to do, if we are able to make it happen, we can sample, which creates new images like new tokens in text. And not only that, but also we can say which of the images have high probability and low probability because we know the distribution, if we are able to do. But the challenge is data distribution is extremely complex and high dimensional. And the question is how to build the complex model to fit into the data distribution. So I'll go a bit faster because there are a lot of equations involved. Please note down your questions so that I can give you if you have any doubt. But I'm going to a bit faster. Otherwise I will not be able to finish it up. So score matching is an important concept from where this everything starts. And score matching starts with this particular phenomena, like this any probability distribution. It has numerator and denominator. Numerator is a function, and denominator is a marginal. Marginal means, I hope all of you know probability distributions. These are basically parameter of theta, not independent of x, because these are summation of all x. So on the x side, it has no such boundary, but theta is the parameter. Now this is one of the form factor which we are dealing with, e to the power minus a theta x and z theta. Now if I take this log, it becomes log of qx theta and z theta. Now how score is defined? Score is defined as gradient of this log probability with respect to x, not theta. Right. So this, if I take the vectors coming out all these derivatives, it becomes the scores. And how it is denoted in a symbolic way, it is a grad x log px. So if I take grad x log px of this equation, what is makes it is grad x log of q x theta, and it makes minus x, minus grad x fx. Why only this? Because log of z theta, it is not dependent on x, so it is 0. That means we are cleverly getting rid of this z theta, which is our pain point, because z theta is impossible to know. I don't know the dictionary of images. How to know marginals is not possible to know. And that is the most difficult part. By defining this score, we are getting rid of z theta through our equation itself. It's not of our concern at all. Right. So now imagine, so when I'm saying grad, that means it's a direction. You know, derivative is a direction vector, right? So if we know somehow this is my image direction. Image is not as easy as like this, but conceptually think, if I know that the grad of p log data exists, and if my computational model is going to learn and try to map my grad of log p theta x is similar to p theta x, I am done. Why I am done? Because now I know how p theta is related to p data. So that data distribution in the first slide of the image matching that I showed is not known, but if I know this through this score matching, I'm done. So I have a proxy of p data with respect to p theta, and they are through these direction vectors. But then we need to minimize this difference between this Fisher divergence of log of p theta and p data with respect to grad. Expected under the expectation of p data distribution, which you don't. Now, who is going to give me p data? We don't have p data. If we had that, then the original problem would have been solved, right? Now it comes a following derivation. So this S theta is nothing but this log of P theta is a score, and S is the equivalent of log of P data, grad x log of P data. So if we expand it, so you know that expectation of EP data becomes the integral of P data x, which is very fundamental in nature, means we from statistics. And this is square, so I am just putting S theta square plus S data square, and this 2 is getting absorbed here. So S theta, S data. So because this constant doesn't matter. Now, if I make this particular thing outside, because this data has nothing to do with theta, so I am making data outside, and all the things of related to theta is here, right? So S theta, S data, and S theta square. Now I know that S data is gradient x log of P data. If I take this gradient, what happens? Log x equal to 1 by x into gradient of x. Just expand it. It becomes log x P data into 1 by P data log x P data S theta x. Right. Now, all of you know integration by parts from your high secondary school. So if you take integration by parts, u dv equal to uv minus v du, and here if you consider s theta x as a u, then you can very easily make this particular equations u dv. So this u dv as uv, this is uv, this is uv, right, which goes minus infinity to infinity, and then v du, this minus become plus, here this minus become plus, p data gradient x square log px, because we have du, and v is p data, and I already have s theta x as a gradient of log of x. So gradient of gradient is double gradient. Hence, this is double gradient. And at infinity, I can assume p data is 0. So I can come up with the original expressions that I started with is trace of log of trace of second order derivative of p theta x and first order derivative of p theta x square, right? Plus a constant, obviously due to this, which doesn't matter. Now this particular part is a Hessian, is a double derivative. And this estimation doesn't depend on the partition function, like z theta. So, and it doesn't depend on p data also. So we have come up with a strategy where this complete dependence on the S data is eliminated, and the final equation is only dependent on S theta, which is wonderful. Now neural network can play a role because it's not dependent on S data. This is a marvel. This was in 2005, not recently. This whole story starts from 2005. Okay. Okay. So now we have this three equation in our hand. Now how to compute it? So this particular compute is relatively easy because why? Because this is gradient, and we know how neural network can produce gradient, right? So let's take a very simple example. So this is a simple two-layer neural network, and last layer is f theta, and this f theta is like if my cursor is visible, this f theta x, where we have to the grad of x of f theta is what we have to compute, right? And this is what any neural network f theta is. So this f is modeled by a neural network. So you are giving a forward pass through an input, and you get a f theta x, that we all know. But what we need grad of f theta x, grad x. So how to get that grad x? Back propagate it. You are going to get grad. In the first layer, you are going to get grad of fx, and if I take the negative of it, because this is a negative of it, I am going to get grad fx of log beta x. So this particular part is done. Then I can take a square. This is just one back propagation done. Right? Easy, cool, very good. Now this part. This is a problem. Why? Because now you get this forward pass, get x theta x. You go backward pass, you got first, like the earlier one, you got the first x with respect to x1 in the first node. But I need what? Double derivative. This is single derivative. The one back pass, single derivative. How to get the double derivative? Again, I have to do only that node to be forward pass with this particular thing as an input. I get the effects. I only backpropagate that part. Now I get double effects and all those, similarly all those things. So I need order of D backpropagations. If the D is very high, like for an image, I don't know how many pixels I am going to deal with, then I'm done. Gone. It's not possible. So then again, there's a problem. Even if we get it to the P data, we are landing up in a defined problem. How to solve it? If we are able to project these entire vectors into one dimension instead of these multiple dimensions, then it would have been better, obviously. What is the solution? Random projections. So we started with that particular log p data x and grad log p theta x. Instead of using all these random data or a random direction vector, let's project them into a simple some random directions. So if I take any random directions and if my projections are equal, then I can fairly say, okay, my original data are also going to be equal. And then my neural network is going to play an important role there because this ordered deep backpropagation is not feasible solution. This is another smart trick, right? So then it comes sliced feature dimensions. So this is, if I have to this project into random vector, then my this particular equation looks like this. Now you see that with apart from this p data, this pv comes. From where this pv comes? Because now we need these vectors where I need to project random vectors. The random vectors should also have a project, the probability distribution, no? And that also has an expectation. So this is what pv's expectation is. Now you see this particular thing are getting projected into v, and this particular thing is also getting projected into v. Now this projection difference is what I'm going to minimize. This is where is pictorially defined here. But again, this particular data is not available to us. So if I go by the same integration by parts, then I'm going to get these projections is Vt, again, this second order derivative of V, Px, V, and first order derivative with Vt. Okay, so now this is a projection matrix. So what I'm going to do, this is very fast because we have seen with a neural network how to do it. But this is problematic because it has two V's and second order derivative. Okay, so now second order derivative with two V's can be decomposed in the algebraic phenomena. What is that algebraic phenomena? Any double derivative can be decomposed into multiple single derivative that you know in your high secondary differential math, right? Del square del x is a del x of del x, right? So this is something del x of del x. The first one is the V transpose del x of log p theta x, and then you take the again del x, and then you give the V. Now this is what I have to make for the negativity because f theta x is the log p theta is the negative of f theta x. In the last slide I showed you. So this does the sign conversions with respect to neural network. Now let's see how it happens. So you have this forward pass f theta x, right? And you have the backward pass. So this part is f theta x. Grad 1, autograd dot grad, all these log probabilities samples. This is the energy net, NN sequential that you guys know by now very easily, right? And we have always make it graph true so that this computational graph exists in my memory. So I got this del fx. Now I need this v. Who is going to give me v? I am associating a v here as an additional node in my computational graph, and that gives me my backpropagation to v transpose fx. So this is what the loss looks like. So the vectors are these are random. The torch sums grad 1 that I'm going to get from autograd multiply with vectors, and that's torch norm is my loss. Okay. Now I'm going to get again of that particular elements forward propagate and back propagate. This is my grad 2. Grad 2 is on grad v. So grad v is grad 1 into vectors. So this is grad 1 into vectors. I'm taking autograd of grad. Again, I'm going to get a back propagation, right? I'm going to get del x. And again, I'm going to get v. This is loss 2. So I got loss 1, loss 2. I'm just combining the loss 1, loss 2 and mean. And I keep on doing it. It's fantastic. So this gives my entire training. And once this is done, there's a concept called Langevin dynamics, which initialize this X, because I need to get this initialization X, because P data, this X needs to come from data set, from images. And then I get this P grad X of P xt minus 1. How I am going to get this? Because this is getting trained. This neural network gets trained. Now you remember this training is f theta x. And what is this f theta x? This f theta x is nothing but grad x p theta x. So this is what grad x p xt. So I'm going to get this. I'm just adding this for t minus time and going to get my final sample. This is how sampling works. This is a sampling. And this sampling is called Langevin dynamics. I'm not going to go into the details, but this is called Langevin dynamics. And how it looks like, you see these tiny direction vectors. These direction vectors are the vectors that are coming from log p xt minus 1 grad x. This is what neural network is learning. Neural network is learning direction vectors. Once you add the direction vectors with this ping data, these direction vectors are saying, okay, boss, go there, go there, go there, go there. And this is the iterative, the repeat. So once you go the repeat up to some time, you are going to get into the minimum. And that is what your generation is. It's very simple, very mathematically elegant, neural network trained, and everything is done with that 2005 concept. And if I use this in my data sample like this of image data, score matching, Langevin dynamics, and nothing happens. This was the first thing. After that, model samples are not very good. After so many lectures, so many things, we arrive at a fantastic solutions which are going to get into a neural network domain. But the image space, it is not happening very nice. But it is in other data space, it happens very good. But image space, still there is something which is missing. What is that missing? Now, once you go into the deep, you see that the direction vector that are getting trained by the neural network, they are not very accurate at the between. They are accurate at the corners, at the extreme corners of the images. When there is not overlapping between images and all, they're very accurate. But whenever there is a overlapping and all, they are very inaccurate. But in the sampling stage, when you are giving prompt and neural network and image generator, stable diffusion, something is generating, you don't know now from where it is starting sampling for the image pixels. So you don't know. If the sampling is, initialization is very bad, then you are plotting a local minima, the accuracy drops, generation accuracy drops. And how to solve it? There's a easy hack. The solve is you make them noisy, right? Everything is about noise, right? You have to incorporate noise into the system. So how to incorporate noise? You incorporation of noise in a hierarchical level. First, you gave a gross level of noise, let them accommodate somewhere. Then you give the second level of noise. With the initialization of the first level of noise, it's converging much better. Then third level, much fine level noise, going a very good sample direction. Now, how to codify it? The equation looks like this, where now you are also have sigma in the P. In the earlier slide, there was no sigma, only theta. Now you have a sigma, which is a variable. Sigma says how much noise you would like to incorporate, right? And how to train it? You have the same score matching the way I showed you in the previous slide, but instead of x1 and x2, you also have a sigma to understand what sigma contributes to what kind of score. Is a score for 1, score for 2, score for 3. What is 1, 2, 3? Is a level 1 noise, level 2 noise, or level 3 noise. Now, if I keep my animation, how it looks like, it start with this particular noise and goes here, and that is why it was not doing well in the previous slide. Now you go into the secondary noise, it's converging, third noise is nice. Once it is done, then your images are good. But can we do better? So can denoising autoencoder and score matching be related? So this is a denoising score, right? I'm denoising it in the score derivative space. But you also know there is a concept called denoising autoencoder. Are they related? If so, how? So we know this particular equation by now, that this is the score the grad x log of p sigma x, and this is my neural network, which needs to be trained. And this obviously this equation needs to be minimized, just like a normal L2 norm or Frobenius norm kind of thing. And we know that this is the formulation that we came out of this derivation using this Hessian, right? And these terms you remember, right? And this term was painful because of p theta x, right? Denoising is another way to solve the same thing, like the way we do for the sliced solution. What is the sliced solutions of that V matrix? You remember that projection matrix, the projection lines of the vectors. You project it and see which one, if the projection matches, then the data distribution matches. That was our assumption. Now, is there any other way to do this? So this is one clever way to do this. It's called denoising phenomena, or denoising, leveraging the denoising autoencoding phenomena. So if you have a X as an image, and that image is getting corrupted by noise, this sigma that I told, this is X tilde, right? Now we have P data of X, which we don't know. And even if we have P sigma of X tilde, we also don't know X tilde distribution. Well, who is going to give me world's all level of denoised version of the image? No one is going to give me. So P or data X and P sigma X tilde is difficult to get, is impossible to get. But what is going to get easy is P sigma X tilde given X. Why? Because P tilde, P sigma X tilde given X is our own formulation. Why? It says, how are we contaminating X to get X tilde? What is the formula? How we are inducing noise? That is in our head. So we know this. So this is a typical example. How do you get this? Suppose this is a normal distribution with sigma square as a variance. So I am taking X as a mean, sigma as a variance, and sampling from these normal distributions, and I'm going to get X tilde. It is very easy. Right. Now, if I reformat this particular equation, instead of P sigma X, if I write P sigma X tilde X, then my equation becomes a closed form, which is very easy. Now, the question is, can I write mathematically P sigma X to P sigma X tilde X? Can I just write that? Is it possible? Is this mathematically viable? Okay, I just wake up in the morning, I think this is intractable solution. So I just make it for my easy. So what is the mathematical rigor for it? But on the contrary, if you see DSM, they can also be part of, if I have a particular format of P sigma, right? If I use this particular format, there's a very nice paper by Vincent et al. In 2011, and you can refer to that. Then it can be mapped to denoising autoencoder. So DSM and DAE basically can be mapped to each other. From DSM, we can go to DAE. So denoising cone matching to denoising autoencoder. How we are going to get? If we take a particular form factor of probability distribution of X. So denoising autoencoder is a special case of denoising cone matching with a particular probability distribution. This is just a aside story. You should remember this, because this is something which is going to be useful if you are going to build your own algorithm some point in time for image generation. Okay, but we were in the question that if P X tilde given X and P X, this can be replaceable. And if so, how? This is what our, how they are related. Whether these two equations are at all related or not. Right? Let's see. Okay, so if we expand again this equation, a minus b whole square, a square minus 2ab plus b square, right? We all know. So p theta x square, I am writing as a constant because it is not dependent on theta. I am writing x theta square plus p sigma x tilde x, p sigma x tilde transpose s theta x. And why this equation comes? Because there is a expectation, and any expectation, if you write in the formulation, it becomes summation or integration over x, right? Okay. So what does it says? It says that log grad x log px equal to 1 by px grad x log px2. These are derivative of log px that everybody knows. Now this px cutoff, what remains is I take the grad x outside, p data inside, because the p data is there, p data x. And this p sigma x tilde is nothing but p data x and p x tilde x. These are conditional distribution. How this p x tilde came? Because first x came, then contamination came. If I do these two product, then only I can get p theta x tilde. Because p theta x tilde doesn't there in on Earth. This is what we are creating. And how we are creating? We are creating with this formulation. P data x and p data x tilde given x. So either x is a chain rule of probability into whatever is remaining. Now, if we go this, because this gradient has nothing to do with data, so I'm pushing the gradient to this x tilde here, because x has nothing to do with gradient. So you see, now it becomes, I can also, again, the way I make this log probability to the derivative, I can do the reverse. So now grad of x tilde p x tilde given x can be rewritten as p tilde x tilde given x graded log of p. Now if you take this grad log, this and this cancel and this remain. It's just an algebraic manipulation, like the way you used to do in our high secondaries, right? Okay, so this becomes a now double integral outside. It's a very clean equation. P data x, then p theta x tilde conditional probability and log conditional probability, log conditional probability. So now if I get rid of this equation of integral, it becomes the two expectation with this particular thing, which is very neat and clean equation, right? Oh, sorry. Okay. So now if I expand this particular equation, if I expand it, it becomes this, right? And if you see this particular equation and this particular equation has only one constant, which is extra appearing, right? And if I get rid of this extra, this particular constant minus constant 2 is also a constant. This equation and this equation are similar. This is where our original question was. Can we replace this x tilde with x tilde given x? The answer is yes. And this is the derivation for it. So now you see our life is very simple. We don't know this, but we know this because this is how, maybe this is normally distributed. This is easy. Remember this equation, it will come handy in later. Please remember this equation. So this equation, this x, even we don't know. Earlier way, when we don't know, we project it in the sliced version and take the scored difference. Here we didn't project, but we take the conditional of it. This is the same problem, two solution and two way of looking the solution. Now think how the solutions are coming up so that you can also come up with a new solution. Okay, fine. So what is the training model then? You have this data point, blah, blah, blah. You have this important noise modulation, like these normal distributions. And now you see this very clean objective, which with Langevin dynamics, like the way I showed, you draw Z and you just, once you learn this S theta from this denoising, you just get the samples. New image pixels will be getting generated, new images will be generated. It's a nice clean algorithms in this particular aspect. Okay, great. So what are the tricks? There are some tricks to be aware of. Training is not that easy. So you have to have a noise schedule of sigma n to sigma 1 in a generally in a geometric progression with sigma 1 is sufficiently large. How this noise schedule is going to be effective if there is a comparability to the maximum pairwise distance between the data points, if you can create the noise, because this is in your hand. Use exponential moving average on weights. If you see in the right hand side picture, if you use the exponential moving average, then your network is going to be well behaved in the orange lines. If you don't use, then the training is a bit jerky. And empirically, it is better to parameterize these NCS and these things with sigma S theta x by sigma, so that if it goes to this particular form, then it is getting stabilized. And by now, everyone you know that these time embeddings are going to be part of every unit. This unit is the design where you are going to give a noisy image and the new network is producing the noise so that this noise can be subtracted and get the original image. And this is how this group norms with the times is getting concatenated. And UNet also has this concatenation of one layer to the encoding layer to decoding layer. This is how you can read the papers to know more tips and tricks. But these are the must-have tips and tricks that is being reported in the papers. Now this is how now the images that were not getting generated earlier. So you are going to get nice low resolution images to high resolution images. It's fantastic. So every pixels are now getting generated with defined versions of noises. And these are all unconditional. You see, starting with random noise, we are generating random images. Okay, so this is what the beauty is. Okay, so can we do much better? Random noise to random generations. If I know what I'm going to generate, then what? So it's called classifier guidance. So what is this? So we have this classifier. We know how a classifier is getting built. So we have a probability distributions of images, and every image has a level. And in the classifier, in the forward model, what we are trying to learn, like in ImageNet, AlexNet, MNIST, no, we take any classifier. Is essentially a probability distribution which says that what is the probability of y, the level given x. This is how the classifier is getting trained, right? Now, if we would like to do the reverse, given a classifier, can I get a sample? So how does it look? I want only one dog image, not cat images, only dog image. Now, when I'm saying this as a prompt, the dog images becomes my classifier, right? Now, given that classifier, can I generate image? What is the formulation for it? Right? So here the Bayes rules comes handy. What is the Bayes rule says? Bayes rule says probability of x given y equal to probability of x in the probability of y given x, probability of y. Everybody knows that. See, everything is very fundamental. Nothing is rocket science. Everything comes from first principle. Till now, everything is from first principle. Now, if I take the logarithm of it, and I know for score, I have to take the gradient with respect to x. That is my score definition, right? So if I take the with respect to x, then probability of y becomes 0. And this becomes grad x p x and grad x p of y given x. So now this becomes conditional score because I am giving level. So I need dog image. Dog is my y, and image that is going to be produced by x. So it's a conditional score. This is unconditional score, which you have seen till now. No guidance. Just given noise, random image. Right? Unconditional score. And this is what the gradient of the forward model. What is the forward model? Is a classifier. So if you are building a classifier, then obviously you have this gradient inside your classifier. It has to be, otherwise how classifier is training. So this is already available to you. But if you train the conditional score with this unconditional score and gradient of forward model, what is the problem? The problem is that how much weight that the gradient is a vector. You see, these are the two vector addition. These two vector additions is going to give you the another vector, right? So how much weight that you are going to put into the classifier gradient and how much weight you are not putting into the unconditional. So this is the influence of the classifier. Now the problem is every time you have to, you see this X is a noisy version, remember sigma, because X has to be noised. So your classifier has to be trained for all such level of noises. Is that practical? No. So if you have to train AlexNet, you have trained AlexNet on clean images. But if you have to train AlexNet on all level of noisier versions of ImageNet data, then you are gone. It's not possible. Although the formulations is quite elegant, but practicality there is a problem, right? So what is the solution for this? The solution is classifier-free guidance. What majorly today generative AI in image space is working. This is a wonderful concept. Again, we have this influence of the classifier guidance, and let's come to the base equation again. P of y given x. Let's start with P of y given x now. So it becomes log of, if I take the scores means grad with respect to x, log of P y given x equal to grad x, P of x given y minus x of log ps. This is what the score is, right? Now let's replace this with this. So let's replace this with this one, right? Now if we replace log of px, what is the log of px from here? Log of p x given y minus lambda into x of p of y given x, right? So if I take this lambda out, then x given y minus x of px. Okay. So now it becomes x given y equal to 1 minus lambda into my score and x given y. So these are so if you see, there are two x given y here. One is with lambda, one is lambda is here. Now, how to make this conditioning? This conditioning is very easy now because you are writing the formulation. There is no y given x because the problem was in y given x, because you need to train that y given x, the classifier guidance. Now there is no x y given x. There is only x given y, right? So it's very easy. If you have an influence vector, you just partition it into two tiny vectors, and then one you scale, one you shift, and then this you take this as an initial vector, you scale with something with multiplication, shift with something, and get. So this is how this scale with 1 minus lambda and shift with x given y with lambda plus lambda. This scale and shift, and you are going to get this classifier guidance, free guidance. But there are some guidelines. It's not that whenever you are training with the unconditional score, every time you are inducing classifier free guidance. What is my dog? What is my dog? During training, I'm saying. So drop out the way neural network is training. So this 10 to 20% time y is removed. So 10 to 20% time neural network is trained with classifier less, means normal unconditional score. There is no condition. And how to give the information that I'm not giving any condition during training? There are some special tokens that are being produced. And now the resulting model has a function of both conditional x given y and unconditional x, because it is getting trained with x given y and x both. And during inferencing, you take the score function of conditional unconditional based on the guidance scale. You just give this addition and produce the picture. And this is how OpenAI glides produce images with a prompt like a tinted glass window of a panda eating bamboo. It's taken from their paper, right? So this is the text embeddings, text which is getting embedded with tokens and all, and act as a Y into their generative model, which produce the X. X is the image. This panda is eating the bamboo, is producing. Okay, so now we have learned about discrete settings, like this sigma 1, sigma 2, sigma 3 are the discrete version of the noise. Now, what if, so we have this formula, sigma 1 is less than sigma 2 plus sigma 8. But this is something is finite element which you have to handcraft and say, which is okay, good, very good. But can we do consider a continuum distribution, so continuous distribution? Because if you are able to make a continuous distribution, then distribution becomes a special case of it, right? So how to do that? So that in the gradient field, in our high secondary or in our BTech engineering maths, we know that any function like y equal to fx can be written as a differential of that function as a d of xt as of f of x, f of t xt. What does it mean? It means that instead of having a one single function, I am having a flow gradient flow function, derivative function. And how this derivative function works? If you take an integration, suppose if you start the boundary value from here and sum up all these vectors, right? Then you are going to get these curves. But instead of summing these vectors, if you start from here and summing all these vectors, you are going to get these curves. So depending upon your initialization, if you integrate all this sum of all change, then you are going to get a function. This we all know. This is called ordinary differential equations. Integration of ordinary differential equation. This is in our engineering maths that we all know. Now, how to utilize this concept? So again, say you are starting from very basic. Everywhere we are starting from basic and coming up with an engineering novelty, so that our today's generative AI is getting flourishing. And this is how people are coming up with new ideas. Okay. So what happens in stochastic differential equation is that, imagine a particle here in the left, there's a particle which is in the Euclidean space and moving purely randomly. There is no order in the movement. Anything, anywhere the particle can go in any position in any velocities. If that is a phenomena, if that is a physical phenomenon, how to describe that in mathematical sense? The easy way to mathematical sense description is that we have a dxt, which is change in space. We have a epsilon, which is random move. And we have a dt, which is change in time. So if you have these three things, dx equal to epsilon dt, is a very simple phenomenon, simple equation, very simple equation. You can model such kind of behavior because everything is random here, right? Now that these particular things I already told, you have this variable epsilon, you have this infinitesimal differential on both sides, you have this exponential movement of x, and since x is a random variable at any point in time, x can be never predictable. So this is what we wanted, right? Now the choices. So formulation is okay. Now we have to make some choice. What are the choices? For example, epsilon can come from normal distributed with 0 mean and 1 deviation. Dt can be square root of dt. Why square root of dt? I just come in. This is just a special notation. I'm coming in a minute. So the choice is make the particle flow in a Wiener process. What is the Wiener process? Wiener process says that any state at t plus w and the state t, if I take this difference, then the difference of the state should come from a normal distribution with mean 0 and standard deviation u. This is t plus u and t, standard deviation u. So that dwt, this wt plus u minus wt is a dwt. It follows a normal distribution, right? And the infinitesimal movement of the particle under such law becomes dxt equal to epsilon into dt, which the pictorially says this. Say if you see very elegantly, you're starting with position x0 and you are moving here and there, anywhere. Looks familiar. It's kind of a noise, right? Here and there, but you are bounded. Okay. Now, how to get this boundary? Through variance. So if I take the variance of dxt, it becomes variance of epsilon root dt. And you know that variance of ax equal to s square vt. And due to this s square, this root dt becomes dt. And that is why I chose root dt as a choice, because of my computational tractability. And if I take this particular integration, it becomes t. So t is my final variance. Variance of what? Variance of this particular equation, this particular phenomenon. So this, how much spread that I can have. Okay. Now, if I'm going to get a more generalized version of it, then the total change is going to be, right now it was only from the origin, but origin can be shifted, which is mu t dt, which is deterministic, and then stochastic. So I'm saying that not everything in my stochastic, not the all particle are moving randomly here and there. Obviously it is there, but there are some kind of orderness also. The world is not completely chaotic, but there are some order, which is kind of our Indian constitutions or something like that, right? So we have some order, right? So there is a deterministic and there is a stochastic version of it. And this is where my mu can also take some dependency on xt. So it can also orient. It's not, it has to be horizontal, it can go in any direction. This is the most general form of stochastic differential equations through which a particle is moving in the space arbitrarily. Okay, and this is a very basic how we come here with the stochastic differential equation. Now, what wonders it can do, given that as a precursor. So if this is my equation of my xt, then what I can do is that you remember the noisy process, right? So every noise goes to a particular global noise. This is how any diffusion process works. You guys knows by now. So this can follow a stochastic process. You see, any noise follows this distribution, and this is a continuous distribution. There is no such hand half coded that we in the score earlier score we did. So this particular score things sigma can be through this particular distribution also. Quite fantastic, no? So you have a very random process to stochastic differential equation, and you map that to the score-based diffusion model. Elegant, right? So what happens is that you start with images and going to this particular yellow regions, which is complete noise. The noising process gets a very good mathematical frame, right? So now we have to make some choice. Let mu xt is minus half beta t xt and sigma xt like root beta t. Like the way I took root dt in my simple case, let's accept root dt. Now if I take this choice and if I expand algebraically, so x here is x minus 1, right? We all know what differential is. And dt minus dt is delta t, right? And this xt becomes xt minus 1 because I'm starting with xt minus 1, obviously. And this is d omega t is basically delta t with reference which is distributed normally. Okay. Now, if you can zero means very small timestamp, then I can write that xt equal to this you know right, the 1 minus half beta t. This is if delta t is very small, then it can be right of 1 minus beta t root to the square root. Why? You remember the Bernoulli's theorem or this expansion theorem? 1 minus x to the power minus n, if n is very small, equal to 1 minus nx, right? So if we use this formula 1 minus half bt, then it becomes the root when it is very small, and it remains as it is. And if I take beta t equal to beta bracket t into del t as a notation, then this becomes bt xt and beta n minus t. These particular formulations, I guess all of you know by now that how this diffusion model works. And this is if I take this as a probability distribution, then the probability distribution of the generative model comes from normal distributed to xt with 1 minus beta t minus 1 beta t. This is a widely used diffusion model that you perhaps see in any paper, any paper, or any different paper. So I am saying how to derive this from the stochastic differential equation perspective. So you get a reasoning for it. Okay. How it get. Now the question is, what are the variants? I showed you the variants. So if I take this variances like the way I took the sigma prime given sigma. So this is one way to get this variance through Markov chain. That every next item is dependent on the previous item plus sigma square minus sigma distributed over 1, 0, 0, 1. Now, if you go by this particular activity, you see that sigma is always exploding. There is no control on something because you have this sigma as a different factor here, which is sigma is tilde. So, if the sigma is exploding, it is called variance exploding phenomenon. You cannot control it. So, your noise is exploding. Right. Now, how to resist it? These are also good, but it can be better. So the question is every time we do better. Every time can do better. Then only you can come up with a better solution. Right. So we know that this is the differential equation formula, which is fxdt and lxdp. Right. If I take this, what is the variance of it? The variance of anything is expectation of x minus mean into expectation of x minus mean transform. That I guess you know from basic probability from engineering maths. But there's a very good book. The PDF is available. You guys can read it. Apply differential equations by take care that how this variance evolves. The variance is this pt evolves over time with this formula. Let's take this formula as a gospel. Let's take the given formula. What this formula is having, this formula is having fxt, which is coming here. And expectation of fxt, this is mean. Expectation of any entity is the mean. And x minus m transpose. And this is exactly same. It's just transpose are different. For the sake of similarity, for the sake of easiness, I can only say this is concentrated on this particular entity and this particular entity. This is just the transpose of this in the matrix sense, right? So if I do these particular operations on our case, what happens? What is E of xt for us? We know E of xt is nothing but beta t xt. So beta t xt is beta t m. Xt m is the mean of all x. Done. What is my fxt minus E of fxt? My fxt is minus beta t xt. And E of fxt, I just have derived beta tm. So this is beta tm. And x minus m is already there. And what is my lxt? Lxt is root over beta t. So lxt and lxt transpose. Let me take q as an identity. So this takes my beta t transpose square. So if I just do my algebraic manipulations here, it becomes beta t into identity matrix minus E into x minus m whole square. It's an elegant formula. This formula is giving how my covariances or my variances are exploding or reserving, how they are going over a period of time. So if you see, I can write this particular dpdt as my dvp as beta t into I minus sigma beta t. Why sigma vpt? Because this is nothing but the sigma. This is a variance, right? And if I solve this differential equation takes this particular shape. Don't go by these numbers or the formulas. See, this particular shape is always bounded by Vp0. There is some entity with a boundary condition Vp0, which is giving my guidance. You cannot go unbounded because there is a bound. Because this is a bound, this particular formulation, the way I'm showing in the left hand side, is variance preserving, and this is variance exploding. This is called VE, this is called VP. Okay. And if I take that standard formula for VP in my normal distribution case, what becomes that gamma t x0 sigma square I, where gamma t is this and sigma square is this. And from where this formula comes? This formula comes by solving this differential equation. Okay. But now you just don't derive it. You can derive at your home if you are interested enough. If you are not interested, just see that these are the formulas. Okay. So now we have got these three formulas about variance preserving in xt minus x0 case, and in the stochastic differential equations for score-based diffusion. And given this as a noisy scenario, we need to denoise it. We need to go from noise to image. So if image to noise is a stochastic differential equation, then noise to image also has to obey some kind of differential equation, right? Now this differential equation has invented in 1982 by Anderson. So you see, many of this concept was already there. It is just now has relooked. So one was in 2005, this was in 82. So all these things were there, right? So read old papers also. This gives you a new insight for creating your future, which is yet to be invented. Maybe the clue lies in 1960, 1970, 1990, you don't know. but you don't discard old papers. That is also my one of the message today. So what that paper says if you are doing this kind of forward process in the differential equation domain, then the reverse differential equation is dxt is 1 minus bxt minus bt into gradient of xt pxt. Now in our context, this is core and this is diff, and this is a diffusion term, the noisy term. So you see in the denoising process also there are some noise getting injected, and this is purposefully done. Why? Because so that you can get diversity in the generative model. Now the diversity in the generative model is a today's concept, but in 1982 this was the algebraic formulation which automatically came. At that point in time, there is no diversity in the generative model, there is no generative model. But this equation automatically comes. Now we interpret this equation as a diversity of the generative model because these diffusion terms and drifts are producing diversity at each point in time. You see there are small perturbation. And this small perturbation are due to the Langevin dynamics that I showed in the previous equations in the last few slides before. Sorry. Okay, so now if I have these marginals, means earlier we didn't know these marginals, but we came up with this nice formula of not having the marginals of p delta x, p sigma x tilde, but the conditional marginal, because this we know is normally distributed, we can control them, or Poisson distributors is your favorite Poisson distribution function. And if you remember, I told you to remember this blue thing. If you remember this particular formula of score training, so what this formula now look like with this particular formula that we have right now derived with gamma x0 and all. So after expectation, this has to be this that we have already proved in the last few slides before. And now if I just rewrite this particular formula with this xt equal to gamma t xt plus sigma epsilon. Why this? Because now I am saying that my formula is not normal distributions is mean is gamma t x0 and variance is sigma square identity matrix. So this is the sample becomes this, which everybody knows how to make the sample out of the normal distributions. If I do this algebra of p of xt given x0, how does it look like? P of xt given x0, p is normal distribution, so log goes away because log and exponential goes away. So it becomes grade of xt into gamma x0 by 2 sigma square. If I do all the derivatives and all, this 2 goes away because of the square, and it becomes ultimately epsilon by sigma t. And this epsilon by sigma t is what? Log x, grad x log p xt given x0. That means this one, right? So you see this one goes how cute, small two variable, right? And this is a remembering equation. You should remember this. Every paper start with this relationship. Not every paper, majority of the paper who are relating this score with diffusion model, they start with this formula, and oftentimes students comes to me that how this formula comes. This is the derivation of it. Okay. And if I now don't use this particular score matching, is a arrow to arrow matching, but I can do this one, which is noise cleaning matching, which is one everybody knows today that the diffusion model is a noise cleaner. Now, how diffusion model becomes noise killer from the score matchers? This is the derivation. This is easy, and the assumption is that your normal distributions is there for p xt given x0, right? And this is how today's generative UI is getting trained, actually getting trained, right? And you can even more make it further better, because our insight for every research paper is to how to make it better, where we are making something nonsense which can make sense, or maybe little bit better, lead better, complete better, something, some kind of betterment. So this is you can have additional two terms for perceptual quality, maximum likelihood, because the same distributions are used for two purposes. One is for generation, another one is for sampling, right? Sorry. Okay. So you are training this, and during sampling, you know this is the sampling process from 1982's Anderson paper. And if you just do some algebraic manipulations, you come with this particular formula, which is your final sampling formula. Sampling formula means how the images are going to be generated by the sampler. Samplers are generating images, not neural networks, right? And this is how I told you, Langevin dynamics. This is how the Langevin dynamics works. This dynamics is basically this and these are basically similar. Here, if you see, grad x log p xt minus 1 is just a score here. This is getting trained by neural. Neural network is producing this, and your sampler is